Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss next problem on Thevenin's theorem. You are given one circuit diagram. The question is to find Thevenin's equivalent circuit across terminals A and B. This time, the open circuited terminals are already given and we have to simply find Thevenin's equivalent, that means VTh and RTh for rest of the network that is connected between A and B. There is nothing given between A and B. So in the previous question, we had 8 ohm resistance here and the question was what is the current through the resistance. So in this case, we will just find VTh, RTh, draw the final circuit between A and B and stop. Whenever such is the case, you can directly start with first step. As I told you, the steps will be same. Step 1 will be to find VTh. So we'll first find VTh. We always define VTh across two open circuited terminals across which we have to find Thevenin's equivalent circuit. In this case, these terminals are A and B. So taking positive polarity at A and negative at B, we define VTh, which is sometimes also called VOC because it's voltage between open circuited terminals. Now we will have to find VTh, and if you remember, to find any potential difference between the 2 points, we always start from negative polarity and through any path we travel up to positive polarity, and when we do that we have to collect all the voltages that we come across. This obviously will be the shortest path in which I can travel from B to A, which is negative polarity to the positive polarity. Let us see what all voltages we will come across. The first will be 10 volts. I'll be going from minus to plus, so that's plus 10 volt. I will need voltage across 2 ohm after that. Now to find voltage across 2 ohm, I will need current through 2 ohm resistance. So that's one thing I will need to calculate VTh. Second will be 3 volts voltage source. Now next will be voltage across 3 ohm resistance. So I will need current through 3 ohm resistance like I need current through 2 ohm resistance. But if you observe carefully, because these two terminals are open circuited, no current can flow through 3 ohm resistance because there is no closed path available. So the drop across 3 ohm will be 0. And hence, after considering 3 volts, we will directly consider 5 volts and reach to point A. So basically all I need is current through 2 ohm resistance. Once I get that, I can calculate VTh. So let me define current through 2 ohm resistance. Let me call it as current Ix. I have taken the direction to be downward. I can choose any direction I want. Now let us see how to find Ix. So we'll first find Ix and then we will go on to find VTh. You can apply mesh nodal analysis, or you can simplify the circuit by taking series parallel combination of resistors or using source transformation and so on. So let us figure out what approach we want to use. Now if you observe carefully, the network that is available to us, it looks little big, but it is very simple network if we plan to apply nodal analysis, because there are only two nodes. This is node number 1, the upper entire line will become node number 1 and this bottom line will become node number 2. So if I take this bottom node as the reference node, then I've got just one single node on the top. Let me define this voltage as Vx. And let us see what all branches we have. This is my branch number 1 in which the 9 volts battery is connected. This is second branch 9 ohm. This is 3 ohm. This is 3 ohm along with a current source, and this is 2 ohm and this particular voltage source. You may apply KCL by considering currents in all these branches and find the value of Vx. But the moment you start doing that, you will run into a problem, which is that you can't define current in this particular branch because there is no resistance available in this branch. Hence, even before you plan to apply KCL in nodal analysis, you should quickly recall that one important point we had discussed in one of the problems in nodal analysis, that whenever there's a voltage source between a node and the ground node, in that case, you cannot write KCL, you get the value of the node voltage directly. So Vx will be nothing but 9 volts, plus 9 to be precise, because negative terminal is at the ground and positive terminal is towards the node. So all these branches, 9 ohm, 3 ohm, this 3 ohm with current source, all these branches play no role in deciding this node voltage. So we write Vx equal to 9 volts directly. And once I know Vx, I can easily find Ix also. You can see that this particular voltage is nothing but Vx because this whole is the same node. So this Vx, when the current Ix flows in the downward direction, the drop of polarities will be plus here and minus here. and hence current Ix will be nothing but the potential difference across 2 ohm will be on positive polarity side we have Vx, on negative polarity side it is positive terminal of the battery, so it's 10, so Vx minus 10 divided by 2 because that's a resistance. Vx is 9, so 9 minus 10 by 2 will be minus 1 by 2, which is 0.5 amperes. So we have got Ix equal to minus 0.5 amperes.